Hello, this is shear force and bending moment example problem number 6. And like before, the goal of this example is to draw the shear force and bending moment diagram for the beam that's shown here. In this case, the beam has a distributed load over segment AB, and it has a point load acting at point D. This problem is a little bit different in that there are four reactions, three vertical reactions and one horizontal. And that represents a bit of a difference in that in the past we only had three reaction problems. So the way that I'm going to solve this is break it up into part A, which is going to be to solve for the reactions, and then part B, which will be to actually draw the shear force and bending moment diagrams. So with that, let's go ahead and go to OneNote where we'll start working on this problem. Okay, so the first thing that I do is I recognize that there's an internal hinge at B. And with that internal hinge, that allows us to write an extra equation of equilibrium. So you'll see that I've already broken it down. What I do is I'm going to take a free body diagram for the portion of this beam that is to the left of that hinge. I could do the same thing with the portion of the beam to the right if I wanted to, but it works out to be a little bit more convenient mathematically to use the portion of the beam to the left. So with that, what I know is that there is a shear force that's acting at point B, but there is no bending moment. The bending moment at a hinge has to be equal to 0. So there's an internal shear force there, call it V sub B. I know that I have a vertical reaction here at A. So now for this particular segment, what I can do is I can draw write the equations of equilibrium for this. And if I take the sum of the moments about point B, I'll take counterclockwise as positive. Excuse me, then what I have is I have a concentrated load equivalent here. So that's going to be 1 kip per foot acting over a length of 10 feet. So that's equal to 10 kips. So what I have is 10 kips, and that's acting at a distance that is, let me draw that in blue instead. So that's a distance of 5 feet right there. So 10 kips, 5 feet, and it's positive. Then I have minus R sub A acting over 10 feet, and that should be equal to 0. So when I solve for R sub A, I get that R sub A is equal to 5 kips. Now I could also solve for the shear force at B. So if I take the sum of the forces in the y direction, take that as up, then what I end up with is R sub A minus 10 kips minus V sub B is equal to 0. So I end up with V sub B equal to R sub A minus 10 kips, or I end up with that equal to a minus 5 kips. All right. Okay, so now that I have the reaction at A, what I'm going to do is scroll down and I'm going to look at the free body diagram of the beam as a whole. And now what I can do is I can go in here and I could say that I know that this reaction force is equal to 5 kips already. And I can use that along with my other equations of equilibrium in order to solve for the remaining reactions. So we'll call this R sub C, we'll call that R sub E. There is also an R sub EX here, but hopefully you can all agree that that's equal to 0 kips by observation. So what I'll do is I'll scroll down just a little bit, and the first thing that I'll do is I'll write a sum of the moments about point E. So if I take the sum of the moments about point E, take counterclockwise as positive, that should be equal to 0. So what I end up with there is 12 kips acting at a distance of 8 feet. That's a positive. I end up with R sub C acting at a distance of 16 feet. That's a negative moment. I end up with 10 kips acting at a distance of 8. 16 and 6 is 22, plus 5 is 27 feet. That creates a positive moment. And then I have 5 kips acting at a distance of 8, 16, plus 6 is 22, plus 10 is 32 feet. And that creates a negative moment about point E, and then that goes to 0. Okay, if we do the math on this, then what we find is that R sub C is equal to 12.875 kips, or round that to 4 significant figures, and we get R sub C is equal to 12.88 kips. So that's equal to 12.88 kips. Okay, now I can do a couple of things. I could take the sum of the forces vertical, or I could take the sum of the moments about a different point. I'll take the sum of the forces in the y direction now for this entire free body diagram. Yeah, there we go. Take up as positive, that should be equal to 0. So we have 5 kips acting up, minus 10 kips because it's acting down, plus 12.875 kips acting up, minus 12 kips acting down, plus R sub E is equal to 0. And if we do our math correctly, then we should find that R sub E is equal to 4.125 kips. So up here, this is equal to 4.125 kips. All right, so the extra equation that we get in this example by drawing the free body diagram of the part to the left is called a condition equation. So this equation here is a condition equation, and it is so called because we can only write that equation because of the condition of the fact that there's a hinge at B. So that gives us an extra equation of equilibrium that we can use to solve for that extra reaction force that we have in there. All right, so then in part B, we'll go through and use these reactions to solve for the shear force and the bending moment diagram for the beam.